So this is my presentation on, understanding how ML models make decisions, kind of opening the black box up, if you will. Um, there's some key features here. Different models will give you different things kind of built in for free. Then you can kind of add some stuff on top of that with some different tools that we'll walk through here today. And then finally, kind of at the frontier of everything is this, mechanistic interpretation where you're really getting down into the nuts and bolts and trying to understand exactly what the model's doing underneath the hood. So, why does this matter? First and foremost, if you work in a field where there's, the government involved, sometimes they say, "Hey, you have to tell us what's going on underneath the hood of these models," and if you can't explain what's going on, then we can't use your model. Um, but more, obviously, the law is the law, but more often than not, what it really boils down to is getting that stakeholder buy-in, right? Like if you can't explain what the model is doing, especially to a non-technical audience, getting that trust and adoption is incredibly hard. And even if, you have been consistent over the past, if things look really weird, to be able to walk into a meeting with executives and say, "Yes, the numbers look odd. This is why." That value cannot be understated. It's incredibly important. And then on top of all of that, just as you're updating and mucking around with these models, just being able to look at them and you know get a better understanding of why certain things are happening so you can debug and improve the models over time as well. We kind of already talked about these three big buckets here, so I won't dive too much into them, but there's definitely some great stuff in that the text there. And then let's start with a quote unquote simple model, this Lime thing, where basically you'll have your original dot. And so this will be whatever data point that you're trying to expand, get a little bit more details on. And so what it will do is it'll kind of create some, random points of data around that original, run it through your model again, create a linear regression based off of that, and then figure out what, um, you know, values were or what variables were kind of moving the needle the most. And so it gives you some understanding of, based on this very specific row of data that you're looking at, what might have been driving um, the outcome. Now there's a few things that can crop up, and why this might not always be preferred. There is definitely some randomness here, because of creating random points around that point to get your value. So different runs can create slightly different results. If you average this over tons and tons of runs, you can kind of get around this, but just something to be aware of when you're using this type of tool. So let's dive into XGBoost. This one's a little bit, really what we're going to get to is SHAP, but I think it's worthwhile to go back and revisit XGBoost at a super high level. So you kind of start with one tree, and then as you build out that tree, you're going to build trees afterwards that kind of um, figure out where you went wrong and help you out a little bit. And so this is just a very simple example of that, where we start off with a one split, and then we start adding trees that split on different things potentially, and uh, continue to get our values better and better, or our accuracy better and better. And so you can see in this very simple toy example, after the three trees with one split, we get to the answer that we're hoping for, where we perfectly classify everything. Now, in real life, XGBoost can use a whole bunch of trees. They don't have to split on just one thing, but that's kind of generally the concept. So now that we've kind of refreshed on that, what are some of the built-in features here? We have gain, weight, and cover. And so gain is just did something give you a whole bunch of information? One split help you out a whole bunch. Then how many times was a feature chosen for splits? And then cover, how many samples flow through the split. So are you getting a bunch of things to go through, or is your split cause it kind of like a niche thing that doesn't help the model out too much overall. Now, some big points here. These are all kind of global things, right? They're also, there's no direction to these values just because a specific variable is high in weight or gain doesn't tell you, like, is it good, is it bad to be those things, or is it helping you classify for this or that. Sometimes yeah, the aggregation here is definitely can hide the story. um, and it's nice that it kind of comes for free, but there's probably some better ways out there that we can utilize to help us out. So this is an example of walking through one specific application or applicant, this applicant D, where we're going to kind of see what CHAP would say about which features were most important. So it will kind of go through iteratively all of the variables that are out there. And this is not specifically tied to trees in this example, but just kind of if we only had DTI, which is debt to income ratio, if we only had your income in DTI, if we had your how many late payments in DTI, if we had all three of these variables, how much is DTI adding? And so we kind of weight these different runs, and we'll come up with an average. And then basically for all of the variables out there, you'll get some value. And then for the specific applicant, we'll know DTI made it more likely to default, their income caused that to go down a little bit, and their late payments also caused it to go down. So we have our final value for what we predict, or what our probability is, or prediction for default. So hopefully that was a little intuitive, and now we're going to kind of expand that to the global. So for each of these rows, they'll all get their own values. And what's really nice is, specifically for this kind of D&E rows where the prediction is the same, you actually get an understanding of what drove that prediction, right? And so there are two very different reasons for why we predicted a default, but we can explain that through this kind of process, which is pretty cool and nice. Now, I'm talking about combinations, and if you're talking about combinations, you should always be a little bit worried about the complexity of things. So, it's important to call that out too. If you're just going about it from purely, combinatorics, you're going to get to an infeasible or, computationally intractable solution pretty quickly, where you just don't have enough time or atoms in the universe to even count the number of combinations. But through trees, it's pretty easy. You just kind of follow the tree paths, so that makes computing these not too difficult. And then also there's some other methodologies where you kind of sample um, and get weighted values that you can then turn into SHAP, so you're not computing every possible combination, but still getting a pretty consistent result. Cool. So now we're going to dive into interpreting transformers. I was actually kind of excited to go through this. As a very unique application of transformers, and I think it was interesting to walk through it and try to learn what's going on under the hood. So if we think about the NLP versions of transformers, the first thing you need to note is the vocabulary. So you kind of have to pick what tokens you want to include in your vocabulary, and all of your tokens will map to some embedding space after you've kind of trained your models. But for numbers, that can get a little wonky. How do you include every number in your vocabulary space? Gets a little crazy. So kind of one of the papers that I was looking through found an interesting way of doing this, where you take a linear transformation into your a linear projection into a kind of higher dimensional space. So instead of taking all of the thousands of words that are out there and projecting it down into 300, couple thousand vector representation, you're kind of expanding these numbers into a higher dimensional plane. And they can encode some more information, or at least that's kind of the theory, when you project them up into that space. The other thing is that each of your columns are going to get their own projection. So the same numbers for CLS could mean something totally different from income. They're all learned in a different way and interpreted in a different way. So once we have all of these, columns and transform them into our tokens, we're going to throw them through attention. And so attention, in the classic sense or NLP sense, is hey, I have the word bank, and what does that mean? Because it could mean the riverbank, or I'm going to go deposit something at the bank, and those are two very different, you know, versions of that word, or they mean something very, very different. So attention kind of solves that problem by allowing bank to look at the other words that are around it or coming up to it and decide on which version of the word it should try to actually represent. And so we could do the same thing with tabular data, where we could have, for each row, maybe you have a really high income. And if you have a really high income, maybe your high DTI says something different about you, where you're more of like a business owner potentially. And I don't necessarily want to say you're going to default, because you're not potentially as likely to as someone who had a very high DTI, but maybe less of an income. And there might be other factors that, this could, this attention mechanism could help get a better understanding for. One other thing to note is, in the classic, Chat GPT sense, you're using, a decoder that's going one direction. So your attention kind of can only see what's behind it. It can't see in front of it, because you're generating text, which makes a lot of sense, right? You don't know the exact next word you're going to say until you say it. Where for this particular paper, they're using bidirectional, so the ordering of the columns doesn't necessarily matter. What matters is that they can all see each other and attend to what they need to. So now we're going to get into query keys and values. And so what's going on here is basically for each, when you're going through the attention head, each token is going to get a query, a key, and a value. Queries are like, hey, what information do I need to know in the other rows? What keys are like, hey, what information, if you're going to ask me a question, what information am I going to share with you? Or what information do I have? And then your value is, what do I contribute? So we'll walk through that. Hopefully this visual helps out a little bit. Where first, like if we're just focusing on this DTI token, it would ask the question, or it would query the other ones and say, hey, what information are you guys going to give me? And then um, uh, turn these values into like a softmax, so everything rolls up to 1. And then basically, hey, now the DTI token knows what value, or what values to get. And so the other interesting thing here to note is that it can attend to itself. So it can say, hey, nothing else matters but me. But in this case, income and late payments matter the most for DTI. Once it gets those, then it will use the values and kind of say, here's what uh, what information I'm going to kind of send down the line, if you will. And so the other thing to note is that you can have multiple attention heads in a transformer. In fact, all of the normal transformers today have many attention heads, and they'll all kind of do different things and focus on different aspects. So all of the weights for these query keys and values are are potentially very different for each attention head, and they might be doing something totally different. And figuring out what's going on can become incredibly complicated incredibly quickly. Yeah. So the other thing to note about transformers is they do have this feed-forward neural network that kind of passes things to the next layer. Um, the important thing to note here, I guess the best way this part has been explained to me is that the feed forward neural network is just the the transformer kind of memorizing information. And what the specific transformer has done is for the neural network, it almost sends everything to zero for the most part. And it's just kind of basically saying, hey, the attention layer has figured out who to talk to, and the feed forward neural network is kind of is saying, hey, what do I need to actually remember about this conversation? And so this is kind of a unique architecture, but really the feed forward neural net is just passing the information that's kind of memorized by the model, in your classic sense of, hey, I've read literally every paper in the world, now I can speak English and have a conversation with you. That's kind of the same process going on here. Just what does this information tell me in general, and what do I need to memorize about it? So when I see something new, I kind of have a sense of what these variables mean in the space in which I've been trained. And then the feed forward neural network is where most of the parameters live in general, and this is no exception. So, can attention tell you the whole story? It is sometimes, maybe. um, so it's worth calling out that, if you're just focused on one thing in these very complicated models, you're not getting the complete picture, and it's definitely worth noting. So this is one of the ways in which you can try to break out what's going on under the hood in a transformer. This is attention rollout, basically just figuring out how much each variable meant to the overall model, or from the attention point of view. And so this kind of matrix multiplication will tell you overall which variables influenced uh, things the most. And so that's kind of one way of trying to understand what's going on in these neural networks. Another way is through tracing the full computation. Basically, what this is doing is it's uh, setting some things to zero, your variables to zero, and then walking them up to their actual values, and then based on that, figuring out um, which variables mattered the most. And I think this is kind of all the ways to try to do the full trace through a transformer. Maybe one of the simpler ones. Again, these are very, very complicated models that are very, very hard to understand, and so trying to break them out is a, a barrier in and of itself. But this is another tool in your tool belt to potentially help with that if you ever come across that problem. So, some other things that are out there, and kind of the mechanistic, frontier, is creating classifiers for each of the neural networks and seeing which each of the attention heads, I'm sorry, and then seeing which ones are kind of saying what, based off those classifiers, and um, can kind of help you figure things out. It's definitely interesting. It does take a lot of time, especially if you have a lot of different attention heads. Um, you can set certain attention heads to basically zero and then see what breaks. So you can see if certain predictions break, and there's attention head figuring out the, high income, high DTI thing that I was kind of mentioning earlier. Or, what other things that particular part of the transformer model is solving for you. Circuits is breaking everything out into these like subgraphs. This is probably one of the more advanced things that are currently being talked about, at least from what I could tell, where you're creating these graphs, mapping all of the neural nets as well as the attention heads together, and really getting down into the weeds of the weeds, to try to get an understanding of what the transformer is doing and thinking. Um, and then, you know, there's some other things, sparse autoencoders, but the main point I want you to kind of take away here is that there's a bunch of different ways you can try to understand what's going on in some of these more complicated models. Some are fast, some are easier to understand than others, but the main thing is as a data scientist, you have to put on your data scientist cap and then think through who am I talking to, what level of scrutiny am I going to be under, and if you're talking to the CEO, busting out graph representations of neural networks probably isn't the call. But if you're talking to a Nobel laureate data scientist, maybe it is, and that's the level in which they're going to expect you to be able to explain things. But hopefully, this presentation kind of expanded upon your tool belt, or gave you some things to go look at. But as always, I think we've talked a lot about this in the course in general, is just start simple and then go to the deeper, more complicated methods if you need to. Um, just because something is the you know, pure math version of how this is actually working doesn't necessarily always mean it's easy to explain. And so again, just really harping on know your audience and build these things for them, not just for you. There's definitely some, SHAP can do a lot. It's an interesting thing to look at. Would highly recommend it. Um, and then if you're kind of confused, you can always try out multiple of these methodologies and see if they're all pointing you in the same direction. If they are, it's probably um, the right call or the right variable that's the most meaningful. And then the frontier is out there in those mechanistic ways that I was kind of talking about. But again, those are very on the cutting edge and extremely hard and complicated to understand, especially for the more intense transformers that are out there in the world. And then here's some papers and further reading. Hopefully you liked this presentation. It was kind of interesting to put together. Made me ask a lot of questions. Worked with Claude quite a bit on creating the visuals and trying to make them more intuitive to users. I think I definitely could spend a ton more time on this, just breaking out some of these visuals, making them more intuitive potentially, or diving into some of the questions I might have had. But this was a lot of fun and a cool project to work